Hi, everyone, and welcome back to the Regression and Beyond series. In this video, we're going to be getting into basic introduction to multi-level models, also called linear mixed effect or linear mixed models, as well as kind of a close counterpart to that, linear growth or linear growth curve models. Specifically, we're going to be talking about random intercept models and then the version of what we call a random intercept model in the linear growth model. So per usual, this script file and the data file are linked below, and we will get right to it. So first, once you import the data and have a look at it, you'll see here that we basically have a repeated measures, or as a hypothetical, we can think about it as like a panel design. So say, for example, we were giving a survey to a group of people and we did it from 2012 to 2006. So this is our main dependent variable, and we have 5 years. And then we have one independent variable, and everything is continuous in this case. Now, one common situation that you might be in when you're doing a multi-level model or perhaps switching to a linear growth model, often there's going to be a little bit of kind of data wrangling and manipulation involved. And the main reason why is traditionally a multi-level model approach, which is what we're going to start with, uses data that is in long format. So it goes this way versus data that is in wide format. So right now, the data we have right now is in wide format because we think about it as a dependent variable. In this case, right, we're getting that repeatedly measured. So we get a column for each of those for each year. So the wide format, but what we want is a long format. So something like having our dependent variable in just a single column and then having some sort of new column that's going to say the year. So for this person in 2012, this is what the dependent variable value is, and then so on and so forth. So often there'll be like already be some sort of ID column that's going to uniquely identify. In this case, we'll pretend that we didn't actually have that, but we know that in this case with our data, these are all unique individuals. So we're going to add it as one simple thing that you might have to do, creating an ID variable. Very simple. We're just going to make it be the row number essentially. So from 1 to that row, I'm just assigning a number there. So now that we've created that ID variable, we're now going to use a pivot function. I'm loading the tidyverse here. Technically, you don't need to load the full tidyverse, but often you end up using, or I often end up using a lot of the packages in there. So I'm just loading the whole thing. And we're going to use this specific function called pivot longer because our data was wide. We want to get it long so that we can then estimate that multi-level model. So I'm doing the pivot longer, saying the data, again, our dependent variables, right? They all start with Y. So that's why I'm using that command here. Okay, I want to take all those columns that start with Y. I'm creating this new variable. Again, it's going to be year. So we'll have one column that just has the specific year in it. I'm adding this prefix here just to say, okay, for that name, it's starting with a Y underscore. Basically, we want to get rid of that, right? So that we just have the years in the column. And then we want a single column as our dependent variable that I'm just going to name Y. So once we run that, now you'll see up here we have another set of data. I named it data long. You see the key difference now, even if we pull it up and look at it, right? Now we have multiple IDs, right? For each year, we're going to see that duplicate now that we have things in this long format, and then each year, and then their value. So you'll see the sample size actually changes. Technically, ultimately, the same, depending on how you look at it. So another quick thing we're going to do before I actually estimate this model. Generally, there's different versions you can do of this, but it's very common to grand mean center a predictor. So this is something we did when we were looking at interactions between like two continuous variables. And here it's very similar reasoning. Often the basic reason we're doing this is because we want to make the intercept have some sort of meaningful interpretation, right? So the intercept when x is 0, in this case 0 is then going to become the mean. So I'm creating a centered version of our independent variable. And now we're going to load Lavaan to actually estimate this multi-level model. Again, this would be called a random intercept model. So in Lavaan, the first thing we do is specify our actual model. So before we estimate anything, we're basically just laying out, here's what our actual model is going to be. On the first level, what we think of as within these people across time, right? We've repeatedly measured across year. All I'm having here is a variance, so just a residual variance component. That's level 1. Then when we move to level 2, this is now where we have our added predictor. So for example, it might be some sort of individual characteristic of these people that we've surveyed over time, and we want to see how it relates to this other measure that we've repeatedly measured over time. So first, we're saying that, again, nothing really happens because we're basically just saving that, again, kind of as an object. This is what we want our model to be. And then now we actually take the next step, which is actually fitting the model. So here I'm specifying, okay, that model's that thing that I just named it, MLM. This is the data. I'm specifying what we call the cluster variable. Again, now that we have it in long format, the idea is we have a bunch of observations within people, right? So that would be our clusters. The cluster would be the individual people, and then we have a set of their responses across time. We're going to be using maximum likelihood estimation, and we're going to estimate robust standard errors, all things that we have done before. But just to note, something we'll do here again, using maximum likelihood, we can then test and compare model fits, commonly comparing like an intercept only or a null model. So we can fit the model and then look at a quick summary. So here you'll notice on level 1, and there's no intercept, hence we're actually adding the random intercept. It's only going to show up at level 2, but we do have the variance that we've specified. So that's going to be our level 1 residual variance. And if we jump down here a sec, this would be that level 2, or we call the random variance commonly. This would be that overall intercept. Again, we've centered our main independent variable. So when that variable is at its mean level, this is what the overall across time level of that dependent variable would be. And then our kind of main part here, the main regression, right? Does it relate to Y? And based on this, indeed it does. One common thing to report with multi-level models is ICCs, or interclass correlation coefficients. This one, just to quickly note, I'll just highlight, this is actually a residual ICC. But ICCs, again, in multi-level models, are just looking at the proportion of variance and trying to figure out like how much variance is at one level versus another. So in this case, it's out of the total variation, how much is at level 2. So in this case, it'd be 25%. But here would be the residual ICC. So we're not saying out of all the variance, that's at the dependent variable, that'd be the unexplained variance. And we have a predictor at level 2. I'm noting that briefly just because this can be something, especially if you're doing more of like a model building or trying different models or adding different predictors at different levels, inspecting this residual ICC and seeing if it changes in a way you expect can be pretty notable. Next thing we're going to quickly do is test against the null model, or again, just the intercept only. So this is going to be only the random intercept model. We're not having a relationship between X and the dependent variable in this case. Again, we don't really care about it, but just showing there, we get the estimates. And now we can do a likelihood ratio test like we've done before. And this, again, we find that is significant. So generally, this would support the idea of, okay, our model with that predictor is better, than an intercept, the model with no predictors at all. So it's somewhat meaningful, I guess you could say. It doesn't really prove that your model is particularly amazing, but it's a common first step to really just kind of demonstrate when you're using maximum likelihood estimation. So now we're going to jump to how would you estimate the version of this model, but using growth curve modeling. So in this case, we're actually going to be jumping back to that wide format data. Again, if you were playing around with these kind of strategies, you would be in this kind of scenario where you're probably going to have to switch from one or the other if you want to try out all these things. So real quickly, I'm adding that centered version because I hadn't done that in the original wide format data that we originally imported. So doing that really quick. Now, kind of the main idea of a growth curve model is, one, it's in this overall umbrella of latent variable models, with the idea that there's some main thing that we're theoretically interested in, and it basically kind of manifests itself in things that we can observe, is theoretically kind of the conceptual idea of latent variable models. So in this case, when we think about like a panel design and something over time, we can think about what we call these growth factors, these latent factors, basically more generally just a trend. You can think about it in some sort of trend over time. And like any other trend line, it would basically have two parts, an intercept and a slope. So in this case, we're basically doing that, but just in a latent version. We're creating a latent intercept. And in this case, we're actually not going to do the slope because we want to basically match that random intercept model. We're just having the latent intercept. But it's still this general idea of we're trying to kind of capture this underlying trend. So our underlying kind of dependent variable that we're interested in, and it's kind of manifesting itself across time as we're measuring it. So this is what the first part of the model is saying. This is to say this is a latent factor. Again, it's going to be our intercept. So we're fixing all these factor loadings to 1. So that's going to be our latent variable. And then we're having our main predictor predicting that intercept. In this case, centering, really might not matter that much, but I'm just using it to be consistent with the other one. So again, once we set up and say, okay, this is our model, then we actually have to fit the model. And then we can look at it. So you can see the output is a little different. Again, kind of one of the main things we were possibly interested in, this relationship between X and Y. That's what we're capturing right there. These are all the factor loadings, but can we fix them all to 1? Just to show you. And then we have some variances, which I'm going to be kind of talking about and showing, talking about a little bit more at the end and why that might be valuable to you. Similar to what we did with the multi-level model approach, we could do a similar thing here and kind of test like only a random kind of intercept model, the null model. In this case, I'm adding in saying, okay, basically X has no relationship with the intercept. So that's my null model, just that one difference between models. And then we can say, okay, are they different? So this isn't actually a likelihood ratio test. This is actually a chi-square difference test, but very similar. We actually just look at the differences in chi-square values for each model. And the difference is actually chi-square distributed. And then we can look at it and see if it is different or not. And now I'm going to run through a couple of these commands real quick. Don't really matter too much. Want to get ultimately to this table that I have here at the end. just to show you a comparison. Again, you could use a linear growth, you could use multi-level model. Statistically, they're the same thing. So that's why you're seeing all these same values within variance, between, or we call random variance, one case or the other, and the coefficient. Again, they're practically all identical. You can see some slight differences, but maximum likelihood uses like an iterative approach. So you can actually get some very small differences just to do that. But generally, these are essentially the same thing. Now, notably, how did I get that within variance? Well, that's where if we jump back real quick, is this the right one? I think this is. Okay, so the variances of each of these. So in the multi-level model, we just get an overall, just that residual within, or the level one residual term. Here, we actually break it up and we actually split it up into separate parts. That at times might be meaningful to you, it might not. But I think basically when you're considering, if you were considering which strategy you might want to use, for me, that's been one of kind of the main things. Do you care about getting, do you just want an overall kind of average like you would get? And again, here, they ultimately are the same thing, but one is kind of separating it a little bit more. And there can be cases where you do care about it. So just a quick note kind of down here, but say there was some sort of, I don't know, like a method effect where we were tracking these people, across time and surveying them. And then for 2 years, there was like this big kind of external outside event that we know kind of affected things. Well, what we could do is actually build in a correlation for those 2 years. So saying, okay, we have this other thing going on and we know that it affected things. So we don't want our overall measure of kind of the main thing we're interested in, our dependent variable, to be unduly influenced essentially by that. So that could be one thing that we could do that you generally wouldn't see with like a multi-level model. So if that's something that were of interest for you, then maybe go to linear growth model. But otherwise, I think it largely, your goals, but then largely conceptual preferences. The latent variable thing where, it's something we can't observe that we actually really care about, and it's kind of manifesting itself or influencing these things that we can observe. So that's how we try to measure it, versus multi-level models or linear mixed effect models really become kind of the ANOVA approach, kind of splitting basically into between and within variance. So one last thing to mention that I actually didn't note before, I did these robust standard errors, but with the multi-level model, when we did those robust standard errors, when you have that cluster, those are actually slightly different robust standard errors. So I won't rant about it too much, but just note about that because we've talked about robust, the sandwich estimator for standard errors before. In this case, if you have a multi-level model and then use a cluster version, we actually do a slight tweak to that process. So sometimes they call them cluster robust standard errors, but just wanted to briefly note that. But anyway, I hope you found this helpful and somewhat interesting. And otherwise, I'll see you in the next video and we can maybe get into some more advanced topics in this area. All right, thanks.